Okay, so this talk is about proof analysis with the method CERES, which we been using in Vienna for quite some time now, also quite extensively. And let me start this talk with this well, rather philosophical questions. What is a proof? I think most of us, if not all of us, have a very precise, maybe very precise definition of what a proof is, but all of us probably know what a proof is, right? So we all learned what a proof is, and so we have a very similar view of what it is. But to most people, a proof is probably just something like a verification. So when we look at this here, probably again, most of us will say, yeah, probably this is a proof. So we have below some end sequence, we have some axioms, and in between some rules. And this is what, well, a tree-like structure, so this is something like a proof. And well, indeed, this particular proof is really a proof. It's the tape proof of this end sequence that you can see here. To exist in X, to exist in Y, such that X is not equal to Y and f of X is equal to f of Y. So what this essentially states is that given an infinite tape labeled by zeros and ones, there are always two cells with the same value. And now this particular proof proceeds by a lemma stating that on such a tape, there are either infinitely many zeros or infinitely many ones. Okay, so we have a verification of this statement. So this is this proof. But are proofs just verifications? And this is the whole topic of proof analysis. So what we are dealing with in proof analysis or proof mining. So usually in a proof, you have hidden implicit information, and the process of making this information, which is implicit, explicit, is the process of proof analysis. And we also have computational proof mining, where we are dealing with formal machine-generated proofs. Now, as this session is the cut-elimination Herbrand's theorem session, I have here also the cut rule on the slide. This is one variant of the cut rule. We have a cut on the formula A, such that A is cut out, and in P star and delta star, these are just P and delta after deletion of at least one formula A. And if we now think of mathematical proofs, when we formalize them, a cut just models the application of lemmas. And therefore, the elimination of cuts corresponds directly to the elimination of lemmas. I have here also Gensen's Hauptsatz. And when Gensen proved the cut-elimination theorem, he also gave an algorithm for the extraction, for the elimination of cuts. So the proof essentially is an algorithm. And when we look at real mathematical proofs, we eliminate the lemmas. And therefore, we transform proofs to elementary proofs. So suppose having a proof in, say, number theory that uses topological concepts, when we perform cut elimination on this proof, we would get a proof which is a number theory but does not use anything from topology. And on the proof theoretic side, what's important for us is to have the subformula property. So we want to have a proof such that every formula occurring in the proof is a subformula of the end sequence. And this is sometimes also called an analytic proof. So we want to have analytic proofs. Essentially, this means that everything that is needed to prove a theorem is already contained in the theorem itself. And well, of course, this is an idealization, but cut-free complete calculi can be considered since Gensen as a close approximation. And there are many applications of cut elimination and in proof analysis. So people are dealing with the extraction of programs from proofs based on Gödel's dialectical interpretation, but also the extraction of upper or lower bounds on the quantified variables that occur in a theorem. This is based on Herbrand's theorem, and what we are working on is the extraction of Herbrand's sequence. This is when we compare it to Gensen, it's just a mid-sequence. Now here I have the general problem on this slide. So we have a proof of a scolemized end sequence S, which is in prenex form, as you see here. And the task is then just to find a valid quantifier free sequence of the form S star. S star is called the Herbrand sequence. And well, the formulas in these A's and B's are just instantiations of the quantified formulas here in S above. And well, if our proof of our end sequence S contains only quantifier-free cuts, we can extract this sequence S star algorithmically. And this is why we need cut elimination. So one method to eliminate cuts is, of course, Jensen's method or any other reductive cut elimination method, which can be described as a normal form computation based on some sets of rules. Well, Jensen eliminates cuts by the reduction of rank and grade by always eliminating the uppermost cut. But the computational features are that this method is usually very slow and usually very weak in detecting redundancies. And this is the reason why we here in Vienna work with the cut elimination method based on resolution, CERES. Well, in case you know how the method works, it's all fine, but if you don't know the method, probably the easiest way to describe it is by thinking of just an input proof. So we have a scolemized proof as an input to CERES in LK, for instance. And then what CERES does is it splits the proof essentially in two parts. So we have the first part of the proof and the second part. The first part is obtained by starting from the initial sequence and only considering the part of the proof that goes into the end sequence, which means only the subformulas that are ancestors of the formulas in the end sequence, and also only the rules that are applied on these formulas. By construction, this part of the proof is a cut-free proof because we just ignore everything that goes into cuts. By some other transformation that I'm not going into detail now, we get what's called a proof projection from this part of the proof. So this proof projection of CERES is just a simple cut-free proof obtained from the original proof. And it is a proof of the same end sequence as the original proof, plus some formula, which I call F here, on the right side of the sequence sign. And now this formula is also very important because it's the characteristic formula of CERES, which is obtained from the other part. So we split the proof in two parts, and the other part, the second part, is essentially all the rest of the proof that's left in the proof. So we have everything that goes into a cut. This is the part of the proof with initial sequence going into the cuts, with all the rules that operate on ancestors of cut formulas. And by construction of this part of the proof, as everything in this proof goes into a cut, and the cut cuts out the formulas, we have a derivation of the empty sequence, which means the initial sequence that we consider in this part, so the axioms that we consider in this part of the proof, derive a contradiction, and therefore these axioms or this initial sequence can be combined in such a way that they correspond to a unsatisfiable set of clauses, which in CERES is called the characteristic clause set. Or we can also define this set of clauses as an unsatisfiable formula in negation normal form, and then we're speaking of the characteristic formula F. Now, as this formula or set of clauses is always unsatisfiable, we can always refute it using any theorem prover. And then this refutation is combined with the cut-free part, the first part, projection, in such a way that we get a normal form, which we call the CERES normal form. And this normal form is a proof with, it has cuts still, but they are quantifier-free cuts. And we can then use this output to extract Herbrand sequence. Here I have a CERES normal form, so this is how it usually looks like. We have the characteristic formula F here above. And what I said before is that this formula F is unsatisfiable, which means that we can derive for all x f of x sequence sign, right? So this is derivable. And as this is derivable, also this sequence here is derivable. F theta 1 to F theta n sequence sign is derivable, just following Herbrand's theorem, right? Because if for all x, f of x is derivable, then also we can find instantiations of this formula such that this is derivable. So this is an LK derivation. And then we take here the proof projection P, which is a proof of gamma sequence delta F. And we substitute it n times with all these substitutions coming from the refutation of the characteristic formula. So we have here n such sub-proofs. And we always cut out the characteristic formula instantiated. So we cut out here f theta 1, then here f theta 2, and so on until we are left only with what was the end sequence of the original proof, gamma proofs delta. So this is the CERES normal form. And now if we wanted to extract Herbrand sequence, a very straightforward approach would be to just consider the n sequence, so all the formulas occurring in the n sequence. And then for each formula occurring there, if it's not quantifier free, we trace it back in the proof tree until we reach an ancestor that is quantifier free. And this is just an algorithmic approach to extracting Herbrand sequence. Now, if you look at this structure of its CERES normal form, we will see that all the ancestors of formulas in the n sequence are in these subderivations here, p theta 1, p theta 2, and so on, but never here. Here is no ancestor of that formula. Now, therefore, there is a simplified version of the extraction of Herbrand sequence using CERES method by not constructing this proof, this normal form at all, but just constructing the proof projection. I mean, this is immediate to see here because the ancestors are all in P. So we extract the Herbrand sequence from P, and then the one that we extracted, we just substituted with the substitutions coming from the refutation, right? And then we merge these Herbrand sequence. And this is a simplified version for proof analysis using CERES, and it has some, it is more efficient essentially because we do not have to construct this proof, because as you can imagine, this CERES normal form blows up because we have here n instances of the proof projection. Here I have an interesting application of CERES. This is already from some years ago, 2008. So this is again a proof in number theory that uses topological structures, which is called the Fürstenberg's proof of the infinitude of primes. So this is a rather complicated proof using topological structures. And this proof was analyzed using the CERES method in a, well, it was not an automated way. It was semi-automated. Major parts of the method had to be performed by hand. And what was done back then already was to define the proof, to formalize the proof as a proof schema. So what this is, I will explain in probably 10 minutes or so. Essentially, it's just that we avoid explicit induction. So we do not have an induction rule. Now, so the proof was formalized and analyzed with the CERES method. And the analysis showed that in this rather complicated proof, Euclid's original argument for prime construction could be found. So Euclid's proof was found in Fürstenberg's proof. And something that's called a Herbrand system was obtained, which is, well, because we are dealing here with induction, we don't have Herbrand's theorem and no Herbrand sequence, but there is a way to get some variants of Herbrand's theorem, and we call that a Herbrand system. Yeah, so we do not need the details here. But this was a rather interesting application. And here I have a toy example. This is nothing really deep, but just to show you how the method works. We have here a proof phi of some columnized n sequence, as you see here, with a cut. So this proof has just one cut. This is the first subproof V1, and here we have V2. And in red, I have all the formulas that go into a cut. So CERES takes this proof as input and splits this proof in two parts, the black and the red one, essentially. And from the red one, we get the characteristic formula by just considering the initial sequence, because they essentially derive a contradiction. So the initial sequence that don't go into a cut, and essentially we don't have axioms here. We don't consider the whole axiom, but just the part of the axiom that goes into the cut. And here we have PU, and here we have QU. PU occurs negatively, so we take its negation, and we take QU. And these two sub-branches are combined by binary inference or left. And here we have to distinguish. Now, if this binary inference operates on n-sequent ancestors, we take the disjunction of these two subformulas. Otherwise, we take the conjunction if it operates on a cut. So here we take the disjunction, and on the other subderivation, phi2, we have here again PA and QV. We take both of them. PA occurs positively, QV negatively. Here we take the conjunction because the or left inference operates on ancestors of the cut. And in the end, because the cut rule combines then these two branches, and a cut obviously operates on a cut, we take it again the conjunction. So this is the characteristic formula. I mean, we could also define it as a set of clauses, right? So we would have three clauses here. And well, it's just a matter of taste. I work here with the formula, and this is an unsatisfiable formula. I mean, it's easy to see from this formula that it's unsatisfiable, but this is the general case for any characteristic formula. Now, the proof projection is obtained by considering the rest of the proof, right? We consider the black parts here. So we start with the initial sequence, but we have to be careful because we have to take the other part of the initial sequence into account as well, because otherwise we wouldn't have axioms here. I cannot just take sequence PU. So we have this other part, and this other part that goes into a cut, it's important to always push it on the right side of the sequence sign, as you see here. And whenever I have two such formulas that go into a cut on the right side, I combine them because I always want to ensure there's only one formula on the right side of the sequence sign that is ancestor of the cut. And this is the other transformation I was talking about. I take the rest of the proof, or the part of the proof that is cut-free, plus in the end I have in the end sequence the characteristic formula on the right side of the sequence sign. This is essentially what this here is about. And here's, I'll skip this. Well, here as well, for the other part, phi2, I again start with the initial sequence, and here I put QV on the right side of the sequence sign. And I combine them, and then in the end, because I have a cut, I combine these two parts of the characteristic formula with an AND right inference. So essentially, whenever I have a binary inference rule in my original proof, I have always to check whether it operates on cut ancestors or not. And here, when it does, like here, I always replace it with an AND right inference. Okay, and now when we have the proof projection, we can already extract the Herbrand sequence from this projection. So here, what I do here is I check these formulas for all x px, for all x not px or qx, and exists in y qy. So I trace back these formulas in the proof tree to find their instantiations, right? So here in phi2 star, I already have two of these formulas. I see that here for y, we substitute v, and here for x, we substitute a. And in the other proof, well, in the other part of the proof projection, I see that I get the instance u here for x. So this is how I get the instances from the proof projection. And then these instances, to get the Herbrand sequence of the CERES normal form, which is not constructed here, we need to combine it with the substitutions coming from the refutation of the characteristic formula. Now, because this here is just a simple example, I have the refutation, I think, on the next slide, but it's simple to see that when we substitute for UA and for VA, so if we use this unifier, we can unify and resolve this and, well, refute it. So therefore, we append this substitution to the three substitutions we have here, and we get the Herbrand instances denoted here by h, small h. The Herbrand instance of this formula is, well, a for x, and here also a and a. So this is how the method essentially works, without going much into detail. Here I also have the resolution calculus. Well, essentially you can use any resolution calculus you want. You just need a refutation of the characteristic formula. This is a rather simple one, which we use for another reason. So here we have axioms, which are just the formulas f, that's sequence f, where f is our characteristic formula, but this calculus essentially works for any quantifier-free formula f. And what we do is we decompose this formula. As you see here, we have elimination rules for all the connectives, and then we add just a simple resolution rule, such that we can resolve these formulas. So we take what in CERES, we take the characteristic formula f, decompose it, so we get the clauses well, in essence, the clauses, yes, and then we resolve. And here we have just the example from the refutation from the simple formula that we had in our example. We use this calculus here because this was extended to, as you will see in a minute, to induction, and defining, in our case, a schematic resolution calculus proved to be simpler when we have this calculus here. So, oops, this here. So it is easy to extend this to a schematic case. well, not really easy, but it's simpler than any other that we tried. Okay. Well, and we have a soundness result. So we proved that whenever we have a CERES normal form and we extract from the normal form the Herbrand sequence, then this is the same Herbrand sequence we will get by extracting it from just the proof projection, well, and substituting it then. Okay. And now let's talk about the extensions. The aim of this investigation is to analyze real mathematical proofs. And therefore, we cannot just work with simple, very simple, basic LK. So the first extension was to not extract Herbrand sequence, but expansion proofs, so Miller's expansion trees. This is done because extracting Herbrand sequence only works if the end sequence is in prenex form. So of course, we can always prenexify the sequence, then we have it in prenex form, and then we apply our method, but then we have to transform it back again. So to not do it this way, so without this detour, we just said, okay, let's keep them as they are, the end sequence that are not in prenex form. So we have nested occurrences of quantifiers, and we just extended the method straightforwardly to dealing with expansion proofs. Okay, so this was the first extension. The second one was done because we had a very naive implementation of this method, and then we tried it on real mathematical proofs and nothing worked because we had no equality. So all mathematical proofs essentially we're looking at had some equality rules. So we extended the calculus, so we have LK plus simple equality, and we then used paramodulation in our resolution calculus, and this was also extended then and implemented. And the last extension is still on an ongoing investigation. So most mathematical proofs, I'm sure you will agree, have some inductive step, right? They use induction. And to analyze these proofs, we will have to deal with induction. However, when we have induction in proof theory, well, basically most proof theoretic concepts fail, and so does cut-elimination. We know that there are methods for cut-elimination in presence of induction, for instance, cyclic proofs, but they do not have the subformula property which we need to extract Herbrand sequence. So we always need, after cut-elimination, an analytic proof. And, well, it is also known that there is no Herbrand theorem when we have induction. However, there is a way to get something which is very similar to that. We replace inductive proofs by proof schemata, and then we compute Herbrand systems. And this is also what was done in the analysis of Fürstenberg's proof. So to give you the idea of a proof scheme, I have this slide here. So suppose we have a proof phi of some n sequent S, which is of the form gamma sequent for all x a of x. And suppose now this proof uses an induction rule. And instead of analyzing this proof, we construct an infinite sequence of proofs like this here. We have phi 0, which is a proof of gamma sequent A0. Then we have phi 1, which is a proof of gamma sequent A1, and so on and so on. So we have an infinite sequence of proofs. And each of these proofs is now a simple LK proof, possibly with equality, but without induction. This is the important part. And therefore, each proof enjoys cut-elimination, resulting in an analytic proof, which I call here phi I prime. This means we can perform cut-elimination on all these proofs, and we get an infinite sequence of proofs again, like this here. Now, what the schematic CERES method does is it takes such an infinite sequence of proofs, performs cut-elimination, and as a result, we get, again, an infinite sequence, but now of analytic proofs. A proof schema is a finite description of an infinite sequence of proofs. So when we define this infinite sequence as a finite description, we denote it as a finite description, then this is what a proof schema is. We have parameters, and then we can, given any parameter, evaluate this proof, and then we know which one we're talking about. But this is how the schematic, or the input of the schematic CERES method. And moreover, what we do, we have a schematic input. So we have a proof schema as an input. We perform schematic cut-elimination on this finite description of an infinite sequence of proofs. And then as a result, we get a finite description of an infinite sequence of Herbrand sequence. Because each of these proofs has a Herbrand sequence. The only important thing is that we need a finite description of that. And this is what's called a Herbrand system. Okay. Now, to get to this proof schemata, we have to extend our language. So what we do is we have function symbols, predicate symbols, formulas, and also proofs that are defined by a primitive recursion. So we also have a base case and a step case, and then some call structure, an order on the call structure. So to distinguish general function symbols or predicate symbols with the inductively defined ones, we have defined function symbols and defined predicate symbols. And we distinguish them with this hat symbol. So this is just an example. F hat is a defined function symbol. And we could define it like this. So we say F hat 0 A is A. So this is the base case. And here we have the step case defined by a primitive recursion. So F hat of n plus 1A is G of F hat NA. And here's the recursive call. So from F hat n, we define F hat n plus 1. And now we can evaluate this. This is how we write this. So we say sigma of n is 2. So this means the parameter n is evaluated with 2. This way we get F hat of 2a, which is then G of F hat 1a, which is then G of F hat 0a, and we get G of a. So this is the evaluation of such a defined function symbol. We can do the same for predicate symbols. This just looks a bit more complicated, but actually it does the same. We have, if we start here with the red one with H, we have a base case and a step case. And the step case uses HN in its definition. So again, the recursive call. These are here just predicate symbols. We use here the defined function symbol. And this looks like something as if it was in second order, but it's not, it's first order. But we have these variables, we call them global variables, which we use for some technicalities in CERES, but we never quantify over these formulas. So this is our H, and we can then define another one, G hat, using H hat. So when we do this, we need to consider this order on the call structure. So when G uses H, it has to be bigger in this ordering than H. And this is used so that we can evaluate this. We need to have an order. This here is, I took this example from a CERES example. So this is how the characteristic formula looks in the schematic setting. So this is a schematic characteristic formula. Okay, and now we can define schematic proofs. And the idea here is essentially the same. We have primitive recursion. We have here an unordered infinite set of proof symbols, delta star, and proof symbols are just used to denote proofs, to give names to the proofs. And for a proof schema, we always consider only a finite subset of this infinite set of proof symbols. And we have a partial ordering of these proof symbols such that there's always a maximum element, delta 0, which is the one we start with. Essentially also when we start evaluating proof schema, we need to know where to start. And this is the maximal element. And then we have parameters. I have here global parameters and one active parameter. We could also define this just for one induction parameter, but here it's defined for any number of parameters we want. Important is that the active parameter is the one over which the induction is performed. And now this is a proof schema. It is just a set of these tuples here, where for each proof symbol delta, we have a base case and a step case proof. And well, I have here this nice slide. The base case proof looks like something like this. And what it is, well, we have the end sequence of our proof schema, which is S delta for parameter M delta. The base case proof is a derivation of S delta of the same end sequence, except that the parameter is set to 0 because it's the base case proof. We have as initial sequence some axioms, depending on in which calculus we're working with. So just simple axioms. And here we might have, so this is possibly empty, but we might have initial sequence that are no axioms, but they are end sequence of other proof schemata. So we can use proof schemata in the definition of a new proof schema. This is just the same thing as we had here, where we used H in the definition of G. So we can essentially we can link to other proof schemata. Whenever we do this, we have to take care of the ordering, right? So we have to say that delta, this one here, is bigger than all the proof schemata we plug in here. Okay, so this is the base case, and the step case is almost the same. It is now a derivation of S delta. So again, the same end sequence, except that the parameter M delta is replaced with M delta plus 1. We have axioms, again, initial sequence, there are n sequence of other derivations, and here is the recursive call. So this is the same proof like this one, except that the parameter is not M plus 1, but just M delta. So from M delta, we define M delta plus 1. And well, if we wanted to evaluate this now, whenever we have, we need to evaluate it for a parameter. So we have to say what M delta is. If it's 0, we just take this proof. And if it's not, we take this proof and plug in here the corresponding derivation. I have here a rather simple example. Just a toy example. We have a proof schema D1 with a base case and a step case. And here I have just this one parameter n. There are no global parameters here. This is the n sequence S delta. For all x, P of x implies P of fx. Sequence for all x, P of x implies P of f hat nx. And this f hat is the one we used some slides before, this defined function symbol. Now, as you see, the base case proof is a very simple proof using an equality inference here of precisely this n sequence S delta, except that n is replaced with 0, as you see here. And now the step case proof is the same n sequence, just the parameter is n plus 1. And it uses here a cut on 1, which is this derivation. There's nothing special about it, it's just a simple derivation. And here it cuts with the n sequence from S delta with parameter n. So here I put precisely this n sequence, the derivation of this n sequence, where I have here, instead of n plus 1, I have just n. And this is our proof schema. And if I want to evaluate it, if n is 0, I take this one. If n is 1, I take this derivation and put here the base case proof, like this one. And otherwise, I have to plug it in a correspondingly, right? I have to check that the parameters fit, and I always plug it in. And this is how this is done. This example goes on here, but this is not so important. This is just showing you that when we have another proof schema of another sequence, so this is a bit different now, then in its definition, in its initial sequence, I can use the proof schema that I defined here. So this one. I can use it here, and I say for which parameter, and if I don't say anything, it's just a parameter n. Okay, so this is our example, and this brings me to the end of this talk. I don't have the schematic CERES definition here on the slide because it's just a very technical definition. But as I said, we have a schematic characteristic formula, which is defined using these defined predicate symbols. We then have schematic refutations of this formula. If I go back here, so this was the formula. We refute it using the resolution calculus that an extended version of the one we had before, where we always decompose the formula. So we take this and decompose it. We just need to add rules for defined function symbols. So if we decompose here to h0, then we need a rule that h0 essentially is just this formula here. So this is how the resolution calculus works. And we get a schematic Herbrand sequence. And the method that we presented here in the beginning for proof analysis with CERES without constructing the CERES normal form, also with the expansion proofs, can be straightforwardly extended to the inductive setting. And I'm not the only one working on this. So this precise this methods that I presented here are joint work with Alex Leitch and David Czerna, and we are still working on it. So there's some more future investigation in this direction. Okay, thank you.